जॉइन कर दिया तो जॉइन कर देखिए पहले देखिए कितने कमेंट कर लेंगे हाँ अरे देखा जो भी
चला ये लेफ्ट करो खाओ
तुम पर जाना ओ
Allora, la
हाँ सर देखा चलती सर क्लास सर अपन
So today we will discuss the factors affecting acid hydrolysis and base hydrolysis. Now, if we write a complex like this, and this complex, this is the oxidation state of cobalt is +3. These ammonias are non-living group. And chloride is living group. Here, if you look at the product, the non-living group is retained, but the living group is lost, and another nucleophile, water has entered, resulting in the formation of the product. So we will discuss the nature of living group, nature of non-living group, and nature of the metal ion. If we change these things, how the rate is affected, how the rate of aquation is affected, So this is the factors which affect the rate of acquisition process. Now look at this table. To look at this table. So number one is nature of non-living nature. If we change the nature of non-living group, how the rate is affected in acquisition process. Metal and remaining same living group remaining same increased chelation will slow down acquisition. That means if we increase the size of the non-living group, living group remaining same, if we increase the size of the non-living group, metal ion remaining same, the acquisition rate will decrease. Let us see the table. Look at this table. Ion, temperature 25 degrees Celsius, pH 1, K, rate constants, expressed in second inverse. First complex is CONS3 whole 5 Cl 2 plus. Rate constant is 6.7 into 10 to the power minus 6 second inverse. Another is cis the rate constant is 1.4 into 10 to the power minus 6 second inverse. Then cis the rate constant is 0.67 into 10 to the power minus 6. So look at this data. Here there are 5 ammonia. The rate constant was 6.7 into 10 to the power minus 6. Here 4 of the ammonia is replaced by 2 ethylene diamine unit. The rate constant has decreased. And when 4 of the ammonia is replaced with a triethylene tetramine. What is trine? Trine is, this is trine. Triethylene tetramine. 1, 2, 3, 4. This is a ligand, which is a tetradentate ligand. So ammonia when replaced by ethylene diamine is this. So that is increased chelation in the non-living group. Therefore, rate is decreasing. Why the rate is decreasing? When the chelation is increased. So according to Born equation, higher is the size of the ion, lower will be solvation. So let that calibrate. This is complex A, this is complex B, complex C. So size sequence, C will be greater than, B will be greater than. So according to Born equation, smaller is the size, higher will be solvation. So this is most solvated. This is least solvated. Most solvated are transition state. Least solvated are transition state. So energy of the transition state will be less here. So low EA and high rate. High activation energy and low rate. So this is, since this is least solvated, that means if you compare plot like this, so this is A, this is B, this is. So activation energy. So activation energy will be highest. This is your potential energy. Progress of the reaction. So complex giving product. So this is C is least solvated. Therefore, at transition state, the energy will be highest here. Here it will be energy. Here this is an energy of the transition state. Energy of the transition state low. Therefore, activation energy is here lowest. Therefore, rate high. And activation energy high. Therefore, rate low. Look at the structures of these complexes. This is A. This is B. So C. So this is the side, chilled ring size is here largest. Here NH also come here, NH can come to this position, NH2 can go to this position. So that will develop a new conformer. So ABC, so size of this is largest, so least solvated. Size of this is smallest, so most solvated.
हाँ सर এটা স্যার ফার্স্ট ফ্যাক্টর বললাম
থার্ড লেকচার in case of base heart disease, here we increasing elevation, there will be rate enhancement. In base heart disease, the reverse is the situation, because the First step is formation of conjugate base. So conjugate base, from the conjugate base, the leaving group is repelled, the leaving group is left. So if the chelation is increased, so breaking of the leaving group becomes easier. But what is the supporting data? Look at the base surface of this and this. K2 is equal to KCB. So here the reverse is the situation, because the rate depends on how fast the conjugate base is broken. How fast the conjugate base is broken, rate depends on this Kcv term and this equilibrium constant term. These two terms are important in base surfaces. Therefore, increasing chelation, there will be rate enhancement. Here, increasing chelation, there are rate retardation, but in base surfaces, increased chelation will increase the rate of the base surfaces reaction. So next part is nature of leaving group. So we discussed the nature of non-living group. Now we discuss the nature of living group. So here if you look at the rate, so rate will be equal to Kcb into Kcb complex total into hydroxide total, or K observed is equal to, these things already we have discussed. So Kcb K by Kw. Correct. K by Kw. Hydroxide. So in terms of K observed, this Kcb equilibrium constant equal to K. What is K? K is the dissociation constant of LH proton. K is dissociation constant of NH proton, and Kw is ionic product of water. What is ionic product? Kw is equal to hydrogen concentration into hydroxide concentration. This is equal to 10 power minus 1. And Kcb, the rate constant or the breaking of conjugate base. So, since Kw is constant, at a given hydroxyl ion concentration, the rate will be controlled by these two factors. For base disease, at a constant hydroxyl ion concentration, the K observed value will be controlled by these two factors. One is Kcp, breaking of the rate constant for the breaking of the conjugate base, and K, what is K? K is the dissociation constant of the NH proton. These two factors will control the rate of base hydrolysis. So the second factor, the metal ion remaining cell, non-living group, remaining cell, the living group order is given below. What is the living group order? Nitrate is greater than, iodide is greater than, bromide is greater than, water is greater than chloride, is greater than, chloride is greater than, acetate is greater than, ammonia is greater than, NCS, N-bonded is greater than phosphate, is almost equal to nitrite, nitrite and water. Is almost equal to hydroxide. So this is the living group order. So this living group order can easily be explained easily. So suppose we take three complexes like this. I can give you the rate constant data. Or complexes like this, CO, NH3O5 iodide 2 plus, CO, NH3O5 bromide 2 plus, CO, NH3O5 Cl2 plus, CO, NH3O5 chloride plus. The aqueous rate constants values are 8.3 second inverse, 8.3 into 10 to the power minus 6, which is 6.3 into 10 to the power minus 6. This is 1.7 and 10 to the power minus 6, and this is 0.086 into 10 to the power minus 6 second inverse. So look at these four complexes. The first one is pentamine iode of cobalt 3 ion. Oxidation state of cobalt is +3 here. Or everywhere the oxidation state is +3. So iode complex is aquated at a faster rate. much faster than the fluorocomplex. What is the reason? The reason is, if you look at cobalt-3 iodide bond will be longest and cobalt-3 chloride bond will be shortest. Cobalt-3 iodide bond will be longest and cobalt-3 chloride bond will be shortest. Therefore, here less energy will be required to break the bond. Less energy will be required to break the bond. Here more energy will be required. So activation energy here will be low. Activation energy will be high. Because here the cobalt-3 iodide distance is large, therefore to break cobalt-3 iodide bond, less energy is required. So activation energy will be low. Here cobalt-3 chloride bond is shortest, therefore more energy will be required. So activation energy will be high. So high rate constant, and here we will have low rate constant. So therefore here the rate constant is highest, here the rate constant is lowest. लिवेदा पिला लेक्चर टाइम लगता है तो एक बैठा है Now let us look at these systems. The N-boded NCS minus phosphate nitrite hydroxide. Here the rate of oxidation will be extremely slow. Now why the rate is slow? Now these are the living groups, this and this. They can form pi bond with the metal. Cobalt-3 system. So pi bond formation with the metal is possible. The field d orbital of the cobalt can overlap with the p orbital, suitable p orbital of the nitrogen. Field d orbital of the cobalt can overlap with the suitable p orbital of nitrogen. As a result, pi bond formation takes place. So those ligands which can form pi bond with the metal center, the living group, expulsion of living group is not easy. Expulsion of living group will become difficult. As a result, the rate will be low. What about phosphate? If you look at the phosphate, cobalt is in +3 state and phosphate is in -3 state. So Coulombic force of attraction between cobalt-3 and phosphate will be extremely high. As a result, breaking of cobalt-3 phosphorus bond will be difficult. Therefore, the rate of the reaction is low for phosphate also. Now let us look at the counterpart, that is the effect of living group for the base surfaces. Effect of living in base hydrolysis. Now I told you that the rate depends on K. K means dissociation constant of the NH proton. Higher is the dissociation constant of the NH proton. Higher is the dissociation constant of the NH proton. Higher will be the rate of the reaction. group order is bromide is greater than chloride, is greater than ammonia, is greater than azide, is greater than NCS minus, is greater than cyanide, is greater than nitrite, is greater than hydroxide. Why this rate? Why this is the rate of base addition? Now we can explain the rate of base additions of bromide, chloride, ammonia, etc. Looking at if you look at cobalt 3 bromide bond, distance of cobalt 3 bromide bond and distance of cobalt 3 chloride bond. Here this bond will be longer, here this bond will be shorter. So rate will be here more, rate of base addition will be more here, rate of acid addition, base addition will be less here. Leaving group remaining same. Leaving group N5 system. So let us, there are 5 pentagon system, this is also 5 pentagon system, so rate will be high here, rate will be low here.
बॉन्ड का से जितने लॉन्ग हबो से तो वीक हबो
इजीली ब्रेक करियो
आया
इजीली ब्रेक करबा रेट बेसी है ना ऐसा बेसी रेट बेसी नॉन लिविंग ग्रुप रिमेनिंग सेम नॉन लिविंग ग्रुप रे समान रख देला तले केटा कंट्रोल होई कोटा केटा कंट्रोल होई तो तापर कहां पर डिपेंड करो केसीबी ऊपर डिपेंड करो जदि नॉन लिविंग ग्रुप is same for this and this, then the rate will depend on what?
नॉन लिविंग का पेंटामिन ग्रुप दिता
pentagon. Suppose this is pentagon, this is also pentagon, this is also pentagon. So two conjugate, theta conjugate base formation. What are the conjugate base? Look at what are the conjugate base? The conjugate base will be now this is the conjugate base from this. So the NH2 group can form the sigma donor and sigma pi donor, sigma and pi donor. So it pushes electron to cobalt 3 center, and cobalt 3 bromide bond longer is the metal and living group bond. The bond breaking takes place easily. So if you look at this structure and this structure. So this is the conjugate base. Conjugate base from chloro complex. This is the conjugate from bromo complex. So this bond breaking will be easier. This bond breaking will be slightly more difficult. So KCB value will be high here, and KCB value will be low here. Therefore, this complex will undergo base addition at a higher rate. That complex will undergo base addition at a lower rate. Conjugate base, amido group will be formed trans to the living group. But you have to remember, amido group is formed trans to the living group. If the trans position is blocked, then only at the cis position amido group will be generated.
सर ब्लॉक के आ गोटे कथा सर जो सिग्मा डोनर और पाई डोनर सेटा केमति सेटा होची
सिग्मा डोनर यार देखो जदे गोटे बेसिक लिगैंड जते बेसिक लिगैंड तुम करियो तार इलेक्ट्रॉन पुशिंग नेचर बेसी हो यू कंपेयर
NH2 minus तो स्ट्रांग बेस
NH3 and NH2 minus. Since ammonia is a weaker acid, its conjugate base will be very strong. So it electron donate करियो cobalt 3 center को electron donate करियो pi bond में रख करियो एटा CR फील्ड p orbital अछि So field p orbital यार vacant Eg orbital संगे bond कर दे pi bond के तरह octahedral complex रे pi d pi bond formation नहीं पाए. So the K value remaining same, higher will be Kcp, higher will be the rate of the base synthesis reaction. Next, third point.
दीदी लगा गला बेस साइड में सुन दीता एस साइड में दीता पॉइंट
Because this is a very simple question. In any interview, this question can be asked. Yeah. Third one. Nature of metal ion remaining same. Nature of non-living group remaining same. Cis isomer will activate at a faster rate than trans isomer. Nature of metal ion remaining same. Nature of non-living group remaining same. Cis isomer. Nature of metal ion remaining same. Nature of non-living group remaining same. Nature of cis isomer will activate at a faster rate than the trans isomer. What is the meaning of that? Let us look at the table. Ion pH1, temperature 25 degrees Celsius, rate constant in second inverse. ठीक लगी देखा
कौन सा देखा
let us compare these two systems and these two systems. Now this is our cis isomer. When during activation reaction at the rate determining step, if the leaving group is lost, at the rate determining step, the leaving group is lost, then what you get? You get so these sigma bonds, metal ligand sigma bond is formed by the overlap of vacant D2sp3 orbital of the metal and filled sigma bonding orbital of the ligand. The metal ligand bonds are formed by the overlap, according to valence bond theory, metal ligand bonds are formed by the overlap of vacant D2sp3 orbital of the metal and filled sigma bonding orbital of the ligand. Maybe
Living.
3p. For here chloride 3p orbital. Because particle configuration of chloride 3px2, 3py2, 3pz2. This is the electronic configuration of chloride. Inert gas configuration we have not written here. So here, so when one of the chloride is lost, this is square pyramid. Transition state, it may be transition state or intermediate. So this chloride has filled 3p orbital. It can form pi bond. The filled p orbital, p pi orbital, filled p pi orbital can form pi bond with the vacant D2sp3 orbital of the metal atom. So therefore this intermediate transition state will be stabilized. So this is stable transition state or intermediate. Therefore energy will be lowered. So energy will be lowered means activation energy will be lowered. Activation energy will be lowered means rate will be high. Let us explain it with the help of one example. Take water. So this is the model. Look at, this is the model. One living group is here, another living group is here. Cis complex, the chlorides are closer to each other, so this is a cis complex. You have one ethylene diamine unit here, another ethylene diamine unit here, cis complex. If the chloride is lost, one of the chloride is lost, there is a vacant D2sp3 orbital here. Vacant D2sp3 orbital of the metal. The vacant D2sp3 orbital can overlap with the filled p pi orbital of the fluoride. Therefore, a pi bond formation is possible. Filled, if this is z axis, then filled pz orbital. Filled pz orbital of fluoride will form pi bond with the d2sp3 orbital. As a result, the intermediate will be stabilized. But this type of situation is not possible in trans isomer. So if you look at the trans isomer, this is trans isomer. This is trans isomer ethylene diamine unit, one ethylene diamine unit here, another ethylene diamine unit, one chloride up, another chloride down. If one chloride is lost, so suppose one chloride, this chloride goes out. If this chloride goes out, look at it. If this chloride goes out, if this chloride goes out, then d2sp3 orbital is here. Vacant d2sp3 orbital will be here. Now the pz orbital, filled pz orbital will be here. This is sigma. This is another p orbital will be here. Another p orbital will be here. If this is pz orbital is involved in sigma bonding. So px and py, these orbitals, filled px and filled py, they cannot form pi bond with the vacant d2sp3 orbital. Pz orbital is filled pz orbital of chloride is involved in sigma bonding, and filled pz orbital of chloride overlaps with the vacant d2sp3 orbital of cobalt 3 forming sigma bond. So which orbital is available for pi bond?
Px and
3py and 3px. So these orbitals cannot form pi bond with the d2sp3 orbital. Therefore, in the square pyramid intermediate, this is square pyramid intermediate. In square pyramid intermediate, pi bond formation is not possible. But in trigonal bipyramidal arrangement, what is trigonal? So if you look at, if you take a trans isomer, this is trans isomer. If one chloride is lost, vacant d2sp3. So filled p pi orbital cannot overlap with the vacant d2sp3 orbital of cobalt 3. Therefore, the intermediate is not stabilized. So intermediate square pyramid intermediate is not stabilized. So therefore, what will happen? It will isomerize. It will isomerize to trigonal bipyramid intermediate. But how the pi bond formation is possible in the trigonal bipyramid intermediate? To TBP intermediate. this is vacant dx square minus y square orbital. This is field px or py orbital. So field px or py orbital can overlap with vacant d2sp, vacant dx square minus y square orbital of the metal for the py. In TPP, in your TPP, the habitation is dsp3. So which d orbital is involved? dz square orbital is involved in habitation. So therefore, the metal will have a vacant dx square minus y square orbital. So metal vacant dx square minus y square orbital can overlap with px or py orbital, stabilizing the trigonal bipyramidal intermediate. But for isomerization, energy is required. From square pyramidal to trigonal bipyramidal intermediate, energy is required. Therefore, a trans isomer will react at a slower rate. Here rate constant is decreased. Trans isomer reacts at a slower rate in comparison to this cis isomer.
सर इटे जो जाउची आइसोमराइजेशन होची तापे को टेंपरेचर हाई करे पड़ियो ने कोन ना
इटा टेंपरेचर हाई नो एटारू एटा कन्वर्सन हेले जाय कि इंटरमीडिएट स्टेबलाइज हे करे।
हां केमिटा कन्वर्सन हो
ऑटोमेटिक ही जो
ऑटोमेटिक
हां किने गोटे लेस स्टेबल मोर स्टेबल रु लेस स्टेबल रु मोर स्टेबल गले एटा एनर्जी एटा मोर स्टेबल है ना एनर्जी कम अछि एटी एनर्जी बेसी अछि सो exothermic process are thermodynamically favorable. So this to this isomerization is thermodynamically favorable. Kinetically also favorable. So this to this isomerize is. किंतु isomerization required energy. Kind एटा TB भी अछि ना एमटा स्ट्रक्चर ला एमटा अछि एमटा स्ट्रक्चर एटा एमटी स्ट्रक्चर एमटा अछि स्ट्रक्चर एटा कन्वर्ट हे जो एमटे and then so it isomerize energy दरकार पड़े
एटा की इंटरेस्टिंग माने लागो जेमति कि ट्रांस का हो नाही
ट्रांस का पाइवट कर
नाही
ट्रायगोनल बाइपिरामिडल इंटरमीडिएट
हां
का इमीडिएट तो ऑक्टाहेड्रल कॉम्प्लेक्स अछि ऑक्टाहेड्रल कॉम्प्लेक्स में लिविंग ग्रुप जब पड़ेला कोन इमीडिएट ट्रायगोनल बाइपिरामिडल हम
हे पार नाही
फास्ट स्टेट होची ट्रायगोनल बाइपिरामिडल स्क्वायर पिरामिड
स्क्वायर पिरामिडल होसी
फास्ट स्क्वायर पिरामिडल हां ml6 रो देखो ml गोटे ए कॉम्प्लेक्स ऑक्टाहेड्रल कॉम्प्लेक्स गोटे लिविंग ग्रुप पड़ेला
स्क्वायर पिरामिडल हे
स्क्वायर पिरामिडल हो
हे पार सेठी माने
स्क्वायर पिरामिड एठी भी होची एठी भी होची उभय केस रे
होची
एठी किंतु स्क्वायर पिरामिड इंटरमीडिएट स्टेबलाइज होची एठी हे पार से लगे एठी रेट कम अछि एठी रेट ता बेसी फास्टर है
एटा थर्ड फैक्टर एसिड हाइड्रोलिसिस तो
एसिड हाइड्रोलिसिस थर्ड मतलब बेस हाइड्रोलिसिस क्या बेस हाइड्रोलिसिस उल्टा
सबुटा उल्टा हो
उल्टा अधिकांश उल्टा मतलब लगा लुक एट द बेस हाइड्रोलिसिस Look at this data. Cis CO En whole 2 Cl2 plus KOH K2 second order atmosphere mole inverse second inverse beta. Here it is 15.1 here the rate constant is 85. Here the rate constant is trans isomer is greater than this is isomer. Why this is happening? Here in base is reverse in this situation. The trans is undergoes base is faster than cis complex. Why this is happening? So this is the conjugate base. NH minus. So if this is lost, this is living group, this is lost. Another situation, trans.
Hello. ଗୋଟେ ଦେଖିଲୁ ପ୍ଲସ୍ ଟୁ ଫାର୍ଷ୍ଟ ଇୟର ମୋ କ୍ଲାସ୍ ଲାଗି
So look at these two situations. If this is lost, this is the conjugate base. So the living group is at a cis position. So they see NH minus could be either created here or here, same. Anywhere it can be created. So if the living group is lost, then here one of the D2 sp3 orbital will be generated here. So pi bond formation between the field p orbital of the nitrogen and cobalt-free sector is possible here. But here, if this chloride is lost, the pi bond formation is not possible in this square pyramid intermediate. So here in square pyramid intermediate, pi bond formation is not possible in case of cis system. Pi bond formation is possible in case of trans system. Therefore, trans rate of base addition of the trans isomer is higher than the rate of addition of cis isomer. Fourth point. same. Nature of living group. Remaining same. The oxidation state of the metal ion remaining same. The rate of accretion follow the order. Chromium 3 is greater than cobalt 3 is greater than ruthenium 3 is greater than rhodium 3. Nature of non-living group remaining same. Nature of living group remaining same. The oxidation state of the metal ion remaining same. The rate of accretion follow the order. Chromium 3 will acquire at a faster rate than cobalt 3. Cobalt 3 will acquire at a faster rate than ruthenium 3. Ruthenium 3 will acquire at a faster rate than rhodium 3. Why this is happening? In accretion process and octahedral complex is converted into an intermediate. In accretion process, an octahedral complex is converted into an intermediate. If the loss in crystal field stabilization energy will be high, then rate will be low. In accretion process, an octahedral complex is converted into an intermediate. If the loss in crystal field stabilization will be high, then the rate will be low. Look at this complex. Hexamine quartzian, this is low state. So this will be T2G6, Eg0. So crystal field stabilization energy will be equal to minus 24 degree. For hexamine quartzian, T2G orbital has 6 electron, Eg orbital is vacant. So crystal field stabilization energy will be minus 24 degree. So for each ammonia, it is contribution is minus 4 degree. Because there are 6 ammonia. 6 ammonia minus 24 degree, so per ammonia minus 4 degree. So if you consider this type of complex, the del 0 of chloride is less than del 0 of ammonia. Crystal field splitting of chloride is almost 50% less than the crystal field splitting of the ammonia. So for 5 ammonia, so it will be again, for 5 ammonia, you have 20 dq for chloride, 2 dq. So crystal field stabilization will be minus 20 for 2 dq. Had there been 6 ammonia, it would have been 24 degree. 5 ammonia, so 5 ammonia means 5 into 4, 20 degree for chloride. The crystal field splitting is less than that of crystal field splitting of chloride is less, 50% less than that of ammonia. Therefore, this is minus 24, 22 degree. So this intermediate, this is in intermediate. This is intermediate. So one of the chloride is lost. Therefore, this will be minus 20. So loss is 2D. So loss in the formation of intermediate is 2D. So initial complex, the crystal field stabilization is minus 22 degree. In the intermediate, this is 20 degree. So final state, final minus initial will be, loss will be 2D. So let us consider now the chromium complex. If you consider chromium complex, chromium, this will be D3, so T2G3 Eg0, so this will be 12 dq. So contribution of each ammonia will be, each ammonia ligand will be 2 dq in chromium complex. Chromium is D3 system, so T2G3 Eg0, so it will be minus 12 dq. For contribution of each ammonia will be minus 2 dq. And for the pentamine chloro complex, this will be 11 dq, because for each ammonia there is contribution is 2 dq. When ammonia is replaced by chloride, so crystal field splitting will decrease. As a result, the initial complex, the complex crystal field stabilization is minus 11 dq, and in the intermediate, after the loss of chloride, it will be 10 dq. So loss is 1 dq. So therefore, if you compare chromium and cobalt, chromium complex, the loss in crystal field stabilization is less, but in cobalt complex, the loss in crystal field stabilization energy is more. Therefore, chromium will react faster than cobalt. Chromium will react faster than cobalt. What about ruthenium and rhodium? Rhodium belongs to second transition series. So, first to second transition metal series, the crystal field splitting will increase from 30 to 50%. From first to second transition metal series, crystal field splitting energy increases from 30 to 50%. Therefore, in case of rhodium 3 belongs to cobalt family. Rhodium belongs to cobalt family. Ruthenium does not belong to cobalt family. So, rhodium belongs to cobalt family. So, here, in case of rhodium, their loss will be more, because if 2 dq, here 2 dq will be approximately equal to 4 dq loss. Here, in case of rhodium system, it will be 4 dq loss. Therefore, rhodium will react at a much slower rate in comparison to cobalt complex. We have seen experimental that cobalt complex reactions can be carried out at 50 to 60 degree, whereas rhodium 3 reaction takes place at 70 to 80 degrees Celsius. Therefore, rhodium system reacts slower in comparison to that of cobalt. Now let us look at the base lattices. What is the effect of different metal ion on base lattices? So, effect of different metal ion on base hydrolysis. non-living group remaining same. Living group remaining same. Hydroxide total remaining same. The oxidation state of the metal ion remaining same. The rate of base hydrolysis follow the following order. Ruthenium 3 will be reacting faster than cobalt 3. Will be reacting chromium 3 will be reacting faster than rhodium. There are several factors which are controlling the base analysis. K exchange of hexamine metal ion, unity, mole inverse, which is 600, which is 1.6. Mole inverse, second inverse. 10 to the power minus 6. So K exchange is related to K exchange is directly proportional to K. K exchange is directly proportional to K means acidity of the NH proton. K exchange, what is the K exchange reaction? K exchange reaction is so K exchange is directly proportional to acidity of the NH proton. So K exchange is favoring ruthenium 3 ion because we have already said that higher is the K value, higher will be the rate of the reaction. So this is favoring the ruthenium 3 system. Then electron affinity. Electron affinity of ruthenium system is 31, 35.5, 29.6, 29.5, 30. So electron affinity is favoring cobalt 3 system. Electron affinity is favoring cobalt 3 system. Here is the electron affinity, here will be the rate of base axis. Then crystal field stabilization energy, crystal field activation energy, crystal field activation energy, crystal field activation energy is equal to crystal field stabilization energy of the intermediate minus crystal field stabilization energy of the complex. So crystal field activation energy is 8.9. This is 11.48. Here is the crystal field activation energy. Here is the crystal field activation energy. Here will be the rate of the reaction. Because intermediate is more stabilized. If the intermediate is more stabilized than complex, the reaction will be faster. Higher is crystal field activation energy. Higher is the rate. So crystal field activation energy is favoring cobalt and rhodium. Then base service is rate constant. .9, 0.85, 1.7 into 10 power minus 3, 4.1 into 10 power minus 4. So here, base service rate constant of ruthenium is highest. If all these three factors are to be taken into account. All the three factors are, when all the three factors are taken into account, it is seen that the ruthenium 3 base service rate constant is 4. Second order rate constant 4.9. This is 4.1 into 10 power minus 4. So all these three factors, electron affinity, K exchange, and crystal field activation energy, all these three factors when taken into account, this is the final rate of base services of different metal ions. Different metal ions containing non-living group and living group. So these are some common situations for acid additions and base additions. Then we will consider another system where we will consider only acquisition reaction, not base addition. Substitution at the carbon on the non-living group increase the rate of accretion. This suggests the fact that process is dissociative. Of this type of complex, trans So this is ethylene diamine. This is 1,2-diaminopropane. 1,2, the carbon number 1, carbon number 2, carbon number 3. So 1,2-diaminopropane. Here that is 6.2 into 10 power minus 5 second. And for 1,3-diaminopropane. 1,3-diaminopropane. The rate is 1,000 into 10 power minus 5 second. Well, we take a this is 1,2-diaminoether, this is 1,3-diaminopropane. In case of 1,3-diaminopropane, there is strong rate enhancement. Why this is happening? Why the rate of accretion is increasing? Increasing in a very large magnitude. When diamino system, the between diamine is tends to 1,3-diamino system. So here, cobalt 3. This chelat is 5-membered chelat. 5-membered chelat is more stable than 6-membered chelat. This is 6-membered chelat. This is 6-membered chelat. Five-membered chelat is more stable than 6-membered chelat. Therefore, here the conformational change is easier. This is less stable, less rigid. So therefore, in the formation of intermediate will be easier here in compared to that of here. So therefore, there is rate enhancement, large rate enhancement in case of 1,3-diaminopropane. 1, 2, 3. 1,3-diaminopropane, there is very, very large rate enhancement. So these are some of the factors which affect acidolysis and base hydrolysis. Now, acid hydrolysis is found to be slower, much slower than the base hydrolysis. Acid hydrolysis is much slower than base hydrolysis. So, the rate of base hydrolysis by rate of acid hydrolysis. This factor can change in the magnitude. So K exchange, forgotten, this is M and H plus D minus. See, deuterium. D means deuterium. This rate constant. Therefore, K exchange is directly proportional to K, dissociation constant of the NH. This ratio is very high. Rate of base hydrolysis by rate of acid hydrolysis, rate hydrolysis, base hydrolysis rate constant is much higher than that of acid hydrolysis. Why this is happening? If you consider acquisition process, in base hydrolysis, due to the formation of the conjugate base, is an amido group is electron pushing in nature, very strong base, electron pushing in nature. This pushes electron to the cobalt 3 center, facilitating the breaking of the cobalt chloride. So this type of acceleration is not possible in acid hydrolysis, because in acid hydrolysis acid hydrolysis, if you compare ammonia and amide, NH2 minus amide is more basic than ammonia. More basic. So therefore, it has sigma donating ability and pi donating ability, both. Here, this type of acceleration is not possible with ammonia. Therefore, base hydrolysis is found to be much greater than aqueous or acid hydrolysis. ଆଉ ଅଛି 15 ମିନିଟ୍ କାଳ ହେବ ତ
maximum 10 minutes.
10 minutes.
The meeting will be ended.
the last unit is evidences in favor of SN1 CV mechanism. Evidences in favor of, if you look at the rate law, K observed is equal to KCB into KCB hydroxide proton. This is equal to K2 into hydroxide proton. K2 is second order rate. So if we plot K observed versus Y-channel plot, you should get linear plot. If SN1 mechanism is valid, then you should get a linear plot. When K observed is plotted against hydroxide proton, but that means at different hydroxide concentration you have to calculate K observed, then you should get a straight line, because this is of the form y is equal to mx. In the absence of NH proton, conjugate base formation is not possible. Therefore, K observed versus hydroxide plot should be linear. So for this type of complexes, or the complexes of this type, CO Cn whole 5 bromide minus 3 COCn whole 5 minus 3 trans dichloro-CO-pyridine series. This type of complexes, pyridine, when covalent center is bonded to pyridine, there is no NH proton. There is no NH proton. So these type of complexes, for these type of complexes, conjugate base formation is not possible. Therefore, K observed versus Y-channel proton plot should be linear without passing through origin. So these type of complexes which do not contain any NH proton, K observed versus Y-channel plot should be linear without passing through origin. So this indicates, this is the evidence, one of the very strong evidence in favor of SN1 CV mechanism. The other evidence is So if instead of water we give another nucleophile Y minus, then this type of product formation is also possible. So here complex plus Y minus DMSO product T half is in hours. Complex plus Y minus DMSO, pyridine or hydroxide. T half in meeting. In the absence of water, in dimethyl sulfoxide medium, the rate of substitution is very, very slow. T half like is in hours. But when you give hydroxide or pyridine, the rate is very, very fast. Why the rate is very, very fast? Because the rate is fast. Because here, in case of this situation, conjugate base formation is possible. Here, conjugate base formation is not possible. So therefore, this rate is slow, this rate is high. So hydroxide or pyridine, a base produces conjugate base. As a result, the product is, in both the cases, same product is produced. But here the rate is very, very slow. Here the rate is very, very fast. Because here, in the second situation, conjugate base formation is possible. In the first situation, conjugate base formation does not take place. This is very strong evidence in favor of SN1CB or DCB mechanism. Thank you very much.